because this is actually what the periodic table should look like. The important stuff should be in the center. I'm sorry, let's do that again. There's the periodic table, and this is the perfect stuff right there. These are happy, perfect electrons, not wanting to mix with anything else. And we need to put them in the center of our periodic table for things to make sense. So there's my inert elements right there on the right side of the periodic table. There they are, right here. Helium, neon, argon, krypton. It's not kryptonite, krypton. And there's my biological molecules, hydrogen, carbon, nitrogen, and oxygen. Notice hydrogen is 1 step away from electron perfection. Carbon's 4 steps away from electron perfection. Nitrogen 3 steps away from electron perfection. Oxygen 2 steps away from electron perfection. These atoms are trying to make happy electrons. And so that's why we draw it in this manner. Underneath oxygen is sulfur, and sulfur can be a substitute for oxygen. They share properties. Study volcanic vents. The bacteria that drive the volcanic vents use sulfur as a substitute for oxygen. Oh, this goes on between us and the Big Island, and this is one of the most profound discoveries we've ever found on the planet, and this has huge implications in astronomy. I'll let you guys read all about that. Right. There's sodium chloride. Anybody know what sodium chloride is? Sodium's 1 step away, chloride's 1 step away, each a step away from perfection, but each in a different direction, and we can put them together to make that stuff right there. Okay, table salt, same stuff in the ocean. Sodium's positively charged, chloride's negatively charged, each one step away from electron perfection. Same thing with potassium chloride. You know what potassium chloride is? They call it salt substitute, which is a complete lie because potassium chloride is a salt. All right? And if you're seeing a doctor for any kind of cardiovascular reason, you should probably ask them before you use this stuff right here. But there's potassium chloride. The grocery store knows what this is. Do you? All right. There's magnesium and calcium. Since they're 2 steps away, when they make ions, they make double charges. Calcium ions double charged, magnesium ions double charged. Why? Because they're 2 steps away. Period. All right, let's talk about phosphorus before time runs out. It's a big electron juggler just like its buddy above it, nitrogen. Phosphorus is very important because it makes up something called the inorganic phosphate. That's a horrible word to describe phosphate because phosphate's a very important organic substance, but they call it inorganic because there's no carbon in it. So they'll abbreviate it PI. It's a big conspiracy. Right? PO4, yeah, 3 negative charges. Phosphate is a very powerful mover of electrons. Remember, moving electrons is about energy transfer. So phosphate is essential in energy transfer. Remember ATP, adenosine triphosphate? We'll talk about that next time if I can get a babysitter. Adenosine triphosphate, ATP, the energy currency for the cell, phosphate, all right? Any enzyme that can move phosphate onto or off of a molecule is called kinase. Anything that ends in ase is a protein, and kine comes from kinetic, and kinetic is about movement. And so anytime kinase is involved, phosphate is involved, all right? Now things can move phosphates without being kinases, all right? But anything that's called a kinase moves a phosphate. And we're going to talk about enzymes next time, hopefully if I can find a babysitter.